So, quantum machine learning. You've definitely heard the term buzzing around, but what is it really? Is it this incredible technology that's going to completely revolutionize AI? Or is it just some really complicated hype coming out of Silicon Valley? Well, let's dig in and figure it out.
We always think about AI getting smarter by just feeding it more and more data, right? Bigger models, faster chips. But what if the next giant leap forward has nothing to do with that? What if it actually comes from the unbelievably strange and powerful world of quantum physics?
And look, this is not science fiction. This quote right here gets to the absolute heart of the promise. We're talking about the potential to take tasks that currently bog down our best supercomputers for weeks and just crush them in a matter of minutes. The stakes here are absolutely massive.
And that brings us right to the core of it all, the quantum AI promise. This is the big, bold vision, where the fundamental laws that govern our universe could totally reshape artificial intelligence as we know it.
So what is quantum machine learning, or QML? At its core, it's all about using these bizarre quantum effects, things like superposition and entanglement, to give machine learning a gigantic boost. But here's the thing you have to remember. It's not really about replacing the AI we already have. It's about augmenting it, creating these super powerful hybrid models that give us the best of both worlds.
Okay, so to really get a grip on this, we've got to pop the hood and look inside. What is it that makes a quantum computer so profoundly different from the laptop sitting on your desk?
It all boils down to this: the fundamental unit of information. Your computer runs on classical bits. They can be a 0 or they can be a 1. Simple, right? But a quantum computer, well, it uses a qubit. And a qubit can be a 0, a 1, or, and this is the part that changes everything, it can be both at the very same time. That and both capability, that's the secret sauce.
Now that whole both at the same time idea has a name: superposition. And honestly, the best way to wrap your head around it is to think of a spinning coin. While that coin is spinning in the air, it's not really heads and it's not really tails, right? It's kind of in a state of being both. It's only when it finally lands and you look at it that it collapses into one state or the other. A qubit is exactly like that spinning coin.
And here is where things just get absolutely wild. One quantum qubit can hold 2 states. 2 quantum qubits can hold 4. This power grows exponentially. By the time you get to just 300 qubits, you can represent more values simultaneously than there are atoms in the entire observable universe. Just let that sink in for a second. That is where the so-called quantum advantage comes from.
So why not just go all in on quantum everything? Well, we have to be realistic here. We're living in what's called the NISQ era. That stands for Noisy Intermediate Scale Quantum. Basically, it means today's quantum machines are still kind of small and prone to errors. And that's exactly why the real focus isn't on purely quantum AI, but on these really clever hybrid models, where the quantum computer acts like a specialized coprocessor that you call on for the ridiculously hard parts.
So what does that hybrid partnership actually look like in practice? Well, you can think of it like a 4-step dance. Step 1, you take your normal classical data and you encode it into a quantum state. Step 2, the quantum circuit does its special processing magic. Step 3, you measure the output to get a classical answer back. And then step 4, and this is the critical loop, a regular classical computer looks at that answer and tells the quantum circuit how to tweak things for the next run. It's this constant, elegant conversation between the two worlds.
Okay, so we've seen the mind-bending promise. It's incredible. But now it is time for a serious reality check. Where does all that revolutionary hype stop, and where does the sober reality begin? This is where the story gets really interesting.
So first, let's just recap the promise, the hype. We're dreaming of lightning-fast computation for problems we can't solve today, the power to see patterns hidden deep inside data, and the ability to learn more but with less information, all thanks to these amazing new hybrid systems. I mean, that's the vision that has the entire tech world buzzing.
But then, reality hits. The hardware we have right now is still pretty much in its infancy. It's small, it's noisy, it makes mistakes. Just getting massive amounts of data into the qubits is a huge bottleneck. And here's the simple truth. For most practical tasks you can think of today, your laptop is still way faster. The bottom line is, we are just not there yet.
And hey, don't just take my word for it. The very companies on the front lines building these machines, we're talking Google, IBM, the heavy hitters, they're all pointing to a pretty similar timeline. They figure a true practical quantum advantage for AI is probably still about 5 to 10 years out.
But listen,
A 5 to 10 year timeline doesn't mean everyone is just sitting around and waiting. Oh no, far from it. The crucial groundwork for that future is being laid right now as we speak.
I mean, just look at this. All the major tech players have these incredible platforms out there today. IBM has Qiskit, Google's got TensorFlow Quantum, Amazon has Bracket, Microsoft has QSharp. These are powerful toolkits that let researchers and developers, even students, start playing with quantum algorithms, either on simulators or on actual, real, early-stage quantum hardware.
And this is just so incredibly important. By building the software, by designing the algorithms, and by developing the expertise now, the entire community is making sure that when the hardware finally does catch up, when it becomes powerful and stable enough, we'll be ready to hit the ground running. The experiments happening today are what will unlock the breakthroughs of tomorrow.
So, where does all of this leave us? Let's try to put the hype and the reality together and get a clear picture of the road ahead.
The future that's emerging isn't quantum versus classical, it's quantum and classical working hand in hand. The best way to think about it is like this. Your main classical computer will still do most of the heavy lifting, but it'll know when to call in its quantum coprocessor for those impossibly hard tasks that only it can solve. The future isn't a replacement, it's a partnership. And if we can get this right, the payoff is just enormous. We circle right back to that incredible promise from the beginning, training massive AI models in minutes instead of weeks, solving huge problems more energy efficiently, and maybe most exciting of all, finally tackling challenges that are simply impossible today in fields like medicine, finance, and global logistics.
So that leaves us with one final thought to chew on. Is this whole journey to quantum machine learning a short, explosive sprint to the finish line, or is it more of a long, steady marathon? All the evidence we have today suggests it's a marathon for sure. But it's a marathon where every single step forward is paving the way for the next great revolution in intelligence.